lesson 50 is our topic of conversation today. It's derivatives of composite functions, derivatives of products, and quotients of compositive functions. Basically, we're still talking about product rule and quotient rule, and then we're also, when we talk about derivatives of composite functions, those are functions within other functions, so basically chain rule today. Kind of review of what we've already talked about, and then just kind of expanding on what we've already talked about. So, first thing there, remember using use substitution, take derivatives. And so, when I first introduced a little bit about the chain rule, we talked about that, okay, this is, if we want to take the derivative of y equals e to the 2x. The idea that this is like taking the derivative of e to some power. And so we can think of this as y equals e to the u, where of course u represents 2x. And then what we can do here, if we're looking at each part, is that we can use differentials. The derivative of y is dy. The derivative of e to the u is e to the u times du. In other words, e to the u times the derivative of that u. If we do the same thing over here with u equals 2x, the derivative of u is du. The derivative of 2x is 2, and then times dx, because we're talking about x. If our goal is to find the derivative of this, so that means our goal is to find dy dx, which means we want this equation to be in terms of x and y only. And so you'll notice here that we have e to the u. However, we know that u is 2x. We also have du. However, notice over here, du is defined as 2 dx. And so we can rewrite and replace and say that dy is e to the, instead of u, I'm going to say 2x times du, which is 2 dx. If you take this equation as is and you solve it for dy dx, we already have dy on the left, we can divide the dx over, and so then it becomes dy dx equals e to the 2x times 2, or in other words, 2e to the 2x. And that was one of the ways that we've looked at taking derivatives using use substitution, where you pull out the inside piece and take the derivative of it separately. Now, from the impression I've gotten, most of you will not take that little bit longer way. We usually talk in class, the derivative of e to some power is e to the 2x times the derivative of that power, and the derivative of 2x is 2. And you'll notice that is what matches up with our answer there. Okay, so let's look at some of these examples. And again, it's derivatives of composite functions. As we look at example 1, it's a composite function because there is that polynomial inside the sine function. But again, we're going to pretty much treat it as a chain rule type problem. So, if f of x equals sine of 2x squared plus 4x plus 6, what is f prime of x? So, f prime of x equals, and this is where I would ask, what is the derivative of sine of something? And the derivative of sine of something is cosine of something. So in this case, cosine of 2x squared plus 4x plus 6 is my something. And then, of course, it is the derivative of sine of something is cosine of something times the derivative of something. So what is the derivative of 2x squared plus 4x plus 6? The derivative of 2x squared, multiply that 2 out front, subtract from the exponent, 4x, plus the derivative of 4x is 4, and the derivative of 6 is gone. In terms of cleaning this up, There's not really a lot of cleanup on this one. I think if I was writing it, I would probably flip it around, and I would bring my 4x plus 4 out front. Either way, whether it's out back or out front, that 4x plus 4 is a sum, and it needs to be in parentheses. So I can say 4x plus 4 times the cosine of 2x squared plus 4x plus 6. Either of those answers would be acceptable. If you had a need, there is a GCF of 4 in that 4x plus 4 that could be factored out. But either of those answers would be allowable. Just do note, the parentheses would be necessary in both cases, in both sets of parentheses, that is. Okay, moving along. Example 2. Let g of x equal the natural log of sine x and find g prime of x. So, g prime of x equals the derivative of natural log of something is 1 over something. Traditionally, we've taken the derivative of natural log of x, and we do 1 over x. So since this is the derivative of natural log of sine x, it's 1 over sine x. So derivative of natural log of something is 1 over something times the derivative of something. What is the derivative of sine x? And that is cosine x. So 1 over sine x times cosine x. If you multiply that, can you see how you can multiply that to be a fraction and say that it is cosine x over sine x? And what do we know about cosine x over sine x? Cosine x over sine x is cotangent x. And so g prime of x equals cotangent x. Okay. Hopefully, I feel like this should be very similar to what we've done. So hopefully you're following along, okay? Moving along to my next page where I have example 3. Example 3. H of x equals x squared plus 4x raised to the 100th power. Find h prime of x. Now, what you need to recognize on this one, and hopefully you see it, but maybe you don't, is what our basic function is here. And our basic function, I'm going to do a side note here, is think about it as u to the 100th. In other words, our basic function is something raised to the power of 100. And so if you do the derivative, so d du of u to the 100th, what is the derivative of u to the 100th? And that is 100u to the 99th. So that's kind of the overall function that you have to look at, in case you've missed that. So let me go back to the actual problem now. H prime of x, the derivative of x squared plus 4x raised to the 100th. So think the derivative of something raised to the 100th is 100 times the something, so x squared plus 4x raised to the 99th. So bring the power out front and then subtract 1 from the power. Now, I said something in there, right? So that means now we have to do times the derivative of something. And what is the derivative of x squared plus 4x? And that should be 2x plus 4. Now, again, this is one of those that I guess technically you could leave it. There are some rewrites that could be done, and I'm going to show you a couple of those so you can kind of get an idea. First of all, realize this 2x plus 4. If you see the GCF in 2x plus 4, That would be 2, and if you factor out that 2, there's 2 times x plus 2. And so one of the rewrites, it would be to factor that 2 out and take that 2 out front and multiply it by 100. And so I could write an answer multiplying the 2 by 100, 200, and then times the other 2 pieces. I'm going to go ahead and bring the x plus 2 to the front. So 200 times the x plus 2, and then times the x squared plus 4x raised to the 99th power. That is one appropriate way to leave your answer. And there is one other way that's a little bit different, but I think it's good for you to start to see. And in the first one, we took the GCF of 2 and put it out front. If you notice, the other parenthesis also has a GCF. X squared plus 4x has a GCF of x. Now, the key is it's not just an x because it's coming from a parenthesis that's raised to the 99th. So a technique you can do is you can pull out that GCF of x, but what that means is you're pulling out all 99 x's. So if I keep my 200 out front, and then if I pull out my GCF of x, what I'm pulling out is a GCF of x to the 99th. I would still have a parenthesis of x plus 2. And then my x squared plus 4, since I pulled out the GCF of x, it would just now be an x plus 4 to the 99th. And so that would be another way you could see an answer displayed. Okay, realize I'm not necessarily saying you have to do that, but I think you need to be able to see the equivalence there. And as we do a little bit more simplifying in some of our other examples today, you'll see me do a little bit of the same thing. I think it's on the example on the back. But just being able to realize you can pull a GCF out of a parentheses with a power. It's just you're pulling out that GCF with that power. Okay. Moving on to example 4 when you're ready. So the problems up top were just derivatives of composite functions. So the focus was chain rule. Now we have to focus on derivatives of products and quotients using their rule. So as you look at example 4, notice it's f of x equals e to the x squared plus 1 to the 100. And what I need you to realize there is that there's a product rule happening here. There are 2 functions there being multiplied. I can take the derivative of e to the x, and I can take the derivative of something raised to the 100th. So those are 2 different derivatives. So I am going to have to use the product rule on this problem. And if you notice, that something raised to the 100th means I'm also going to have to use the chain rule. So this problem is a product rule and chain rule problem. So let's hop into it. They give us f of x. We're trying to find f prime of x. So, product rule, derivative of the first, so the derivative of e to the x is e to the x times, and the second part stays the same. So x squared plus 1 raised to the 100. Product rule says we add, and now we flip. We're going to keep e to the x as is, and then now we're going to do times the derivative of x squared plus 1 to the 100th. And what's the derivative of something raised to the 100th? That's going to be 100 x squared plus 1 raised to the 99th. So multiply the exponent out front, subtract 1 from the exponent of the power. Now, notice the inside was not just an x, so we're doing the derivative of the inside. So the derivative of something. The derivative of x squared plus 1 is 2x. And so that right there was my chain rule happening. Derivative of x squared plus 1 was 2x. Now, a couple of cleanup options. One cleanup option that you would be likely to do is to pretty much just kind of leave it as is and just kind of clean it up, take the multiplication dots out, put GCFs out front. So, like in this case, you could say e to the x times x squared plus 1 to the 100 plus, on the second term, there's a 2x out back that could be brought out front, and that 2x could be multiplied by 100. So 2 times 100 is going to be 200. There's an x, and there's an e to the x. So I would probably write this in the form of 200x e to the x, and then times x squared plus 1 raised to the 99th. That is one option. And again, honestly, that's the option you guys are probably going to be more comfortable with, and that's fine. But again, trying to get you to make some connections. And some of the connections we can make here, as you think with the answer I just gave you, think about this as two terms, where the first term is e to the x, x squared plus 1 to the 100th, and the second term is everything else, the 200x e to the x, x squared plus 1 to the 99th. Now, what I want you to do is I want you to think in terms of GCFs. What do those two terms have in common? And so as we think about GCFs, notice both first and second have an e to the x. So we can factor out e to the x. The other piece you'll notice that they both have in common is they both have an x squared plus 1. How many x squared plus 1s do they have in common? And this is where one has a power of 100, the other has a power of 99. And so the lower power, they have x squared plus 1 to the 99th power in common. So the other GCF I can do is x squared plus 1 to the 99th. And so those right there are my GCFs. Now, what I have to do to finish off the problem is, okay, what remains after I factor out those GCFs? So in the first term, we would divide out the e to the x, and we would divide out 99 of the 100 x squared plus 1s, which means how many x squared plus 1s are left? And there would be 1 left. So I'm going to have an x squared plus 1. And then plus, and so now we're looking at the second term. In the second term, notice 200x is still going to be there. I'm going to factor out the e to the x, and I'm going to factor out the x squared plus 1 to the 99th. So once I factor those out, I'm left with 200x. And that would be a way to express an answer as well. Is right there. If you wanted to rewrite that last parenthesis and say x squared plus 200x plus 1, that could be done as well. But you would also be fine to just leave it as you are. Okay. One more. We got one on the back, right? So let's go to that back page and look at it. This time they give us f of t. They ask us to find f prime of t. Okay. As you think through this problem, notice there's a fraction. So that, of course, means we are going to be using quotient rule. And as you look at some of those functions, notice it's sine of 2t. There's something inside. On the bottom, there's something raised to the fifth. So that also means we're going to be talking about chain rule. So we have a quotient rule and chain rule happening within each other. So let's get started here. We're trying to find f prime of t. I will say this one is wide. It takes up quite a bit of room. So hopefully this will work on my iPad here. Okay. And honestly, I'm just going to use the whole paper, the whole screen. Okay, quotient rule. The derivative of the numerator times the denominator. So the derivative of the numerator. The derivative of sine of something is cosine of something. Don't forget right there before you go on, times the derivative of something. So what's the derivative of 2t? And that is 2. So I'm going to go ahead and put that 2 out front of the cosine 2t. Plus, we still have to do the derivative of natural log of t, which is 1 over t. So that right there is the derivative of the numerator times the denominator as is. So t to the third plus 3t raised to the fifth. Then quotient rule says we subtract. And now we're doing derivative of the denominator, keep the numerator. So derivative of the denominator. The denominator is something raised to the fifth. So something raised to the fifth is going to be 5 times something raised to the fourth. Before you move on, don't forget, times the derivative of that something. So what's the derivative of t cubed plus 3t? And the derivative of t cubed is 3t squared plus the derivative of 3t is 3. So that's the derivative of the denominator times the numerator as is. So times the numerator, which is sine of 2t plus natural log of t. All over denominator squared. So my denominator is t to the third plus 3t raised to the fifth. If something is raised to the fifth and then squared, it's now raised to the 10th. Okay, so we have a mess. One option would be to leave it a mess. Some other options, so you can start seeing some equivalencies. Think about this as 3 terms. There's 2 terms on top, the term before subtraction sign, term after subtraction sign, and there's a term on bottom. What do all 3 terms have in common? And they all have a t cubed plus 3t. How many t cubed plus 3t's do they have? We have exponents of 5, 4, and 10. So that means they all have at least how many? At least 4. So one thing we can do here is we can cancel out t to the third plus 3t to the 4th power. So this one right here after the minus sign, we can cancel that out there. Now here's the deal. If you cancel a factor out, it has to cancel out of all the terms. So it cancels out that term altogether. In the first term, t cubed plus 3t to the 5th, if I cancel out 4 of those, that means I have 1 left. In the denominator, if I had 10 and I cancel out 4 of them, that means I now have 6 left. So that's one way that we're going to help clean it up a little bit. I'm going to work on rewriting it now and do some cleanup along the way still. So f prime of t, and let's see. As we look at this first term, notice t cubed plus 3t has a GCF. So I'm going to factor that GCF out, and there's a reason. It's going to be helpful here in a moment. So if I factor that GCF of t out, just put the whole term first, then that leaves in those parentheses t squared plus 3. And then I still have the 2 cosine of 2t plus 1 over t. And we'll talk about, I have one more step after this, we'll talk about how to get rid of that fraction, because that's the piece that they don't usually want you to do, is to leave a fraction within a fraction. Minus on the second half of the numerator. We have the 5 out front, and you will notice that 3t squared plus 3 has a GCF of 3. So I'm going to factor that 3 out, and then I have t squared plus 1 in parentheses, and then I still have sine of 2t plus natural log of t. In the denominator, what kind of GCF do I have in the denominator? T cubed plus 3t has a t in common. Now, if I factor that t out, it's not just a t. That parentheses is being raised to a power of 6. So when I factor that GCF of t out, it's actually a t to the 6th. And then times t squared plus 3 raised to the 6th as well. Now, is that one really cleaning up the denominator a whole lot? Not necessarily a whole lot, but every little bit can help in certain situations. Okay, one last rewrite. A teeny bit of cleanup, and I mentioned earlier that I wanted to get that 1 over t out of there. Notice I just factored a GCF of t out front. That t can multiply by one parenthesis or the other. Well, I factored it out of one parenthesis, and that means that GCF of t can distribute to my other parenthesis, which means it has to multiply by the term 2 cosine 2t, and it has to multiply by the term 1 over t. And so that'll be my last little bit of cleanup there. So t squared plus 3, I'm carrying down. My t out front is going to multiply to both terms in the second parenthesis. So now I'm going to have 2t cosine of 2t plus, and when I multiply t by 1 over t, it just becomes a plus 1. Minus, about the only thing I can clean up on the last part there is 5 times 3 and make it 15. Still times t squared plus 1, and still times sine of 2t plus natural log of t. All over t to the 6th times t squared plus 3 raised to the 6th. And that's the answer that I have set in my notes. Again, important to be able to try and figure out, some of this simplifying, become familiar with it. AP is all about, multiple choice problem. You have to be able to match their form to pick the right answer. So, okay, your homework is problem set 50. In problem set 50, for the moment, skip anything that has to do with problem set 49, which there'll probably be a couple. So skip those, leave some space, whatever. I'll have you go back and do those after I teach lesson 49 on Monday. So, have a good weekend, and I will see you guys on Monday.